Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering, Ajay Kumar Garg Engineering College. Today my topic is Control Unit from the subject Computer Organization and Architecture. My topic covers Introduction to Instruction Codes, Instruction Cycle, Computer Instructions, Hardware Control Unit, its block, its description, and Timing and Control Unit. Now let's begin with what is a basic instruction is and what is the structure of a basic computer system. Now as per an example, we are taking the RAM will be of size of 4096 words in it. So when we simplify this 4096, we will get it in a power of 2, that is 2 raised to power 12. And the 12 bits we will select for a word memory to represent the word memory address. And each word will be of 16-bit long. So we are assuming this RAM to be of 4096 into 16. That means 2 raised to power 12 into 16. This is the size of our RAM memory. This complete RAM memory. And this 12 is actually the address lines, which is equals to 12, and this 16 is your data lines, the size of our data bus. So that's why we are considering our address or address register to be the size of 12 bits and the data register to be of size of 16-bit according to this configuration of the RAM memory, which we are taking as 4096. So program, what is a program? Program is a sequence of instruction, we can say, of a machine. And what is a machine instruction? A group of bits that can tell a computer to perform a specific operation. And the instruction of a program along with any needed data are stored in the memory. The CPU will read the address of the next instruction from the memory, and where we will put the address of that instruction which we are going to execute, that is our program counter, a special purpose register. And after that, when we fetch the instruction from the RAM memory, we will copy it into a instruction register. And the size of instruction for this configuration we are considering to be of 16-bit. As we are taking the size of single word in a RAM memory to be of 16-bit according to this configuration. So that's why the size of IER, that is the instruction register, is also of 16-bit. Now then we come to what is instruction format. A computer instruction is divided into 3 parts, as we can see over here. These 3 parts. First, from bit number 0 to 11, it will be named as address. So this area is reserved for the address of an instruction, the address inside the instruction. And the next 3 bit is from 12 to 14 will be the opcode bit, which is known as the operational code bits. And I here will show the mode bit, that is the bit number 15, the most significant bit of this sequence. So we can say that, suppose we are having here, this is the memory, and we have a 16-bit of instruction in it. This instruction, when we fetch it, will be copied to this IR register. That will be of again 16-bit, and it is its distribution. The address, the operational code bits, and the mode bits. The address will tell us where the opcode actually lie, whether it is directly available or indirectly available, and operation code will tell us which operation we are going to perform on that particular. It will be performed by the instruction on the operands, and the mode will tell whether it is a direct addressing mode or indirect addressing mode, and the types of instruction also depend upon the combination of opcode and the mode bit. So we are having 3 types of instruction: memory reference instruction, register reference instruction, and input output instruction. And how we can segregate them, how we can differentiate them. that will be according to their 16-bit of code. That when the instruction is fetched from the memory to IR, here we have an instruction that will be fetched to an IR register that will be of 16-bit. After that fetching of an instruction from the memory, we will decode it. We will come to know to bet which particular type it will be going to be. Either it will be a memory reference, register reference, or input-output reference. For memory reference instructions, the opcode bit will be the combination from 00 to 110. That means that the opcode may be like this. It may be 000, 001, 010, 011, and so on to binary bit 6. The binary code of binary bit 6. So we have in all 7 memory reference instructions. And here the mode bit I will tell whether it is a direct addressing mode or a indirect addressing mode. If the value of I is 0, then it is a direct addressing mode, and the value of when this I will be 1, then it will be a indirect addressing mode for memory reference instruction. The second type of instruction is register reference instruction. Here the 3-bit opcode will be always stable. That will be only 1, 1 and 1. And on the basis of this, we can judge whether this particular instruction is a register reference or input-output reference. The combination of these 3 bits, opcode bits, with this mode bit will decide the type of instruction among register reference and input-output reference. For register reference, the mode bit will be always be set as a 0. And for input-output reference, the opcode will be same as that of register reference instruction 111, but the mode bit will be 1. So in this way, we can differentiate between the register reference instruction and the input-output instructions by using the concept of this mode bit. For register reference, it is 0, and for input-output reference, its value is 1. Whereas, separating these two from memory reference will include the opcode. Here the opcode value will be from 00 to 6, binary 6, and these both are having the binary code 7, 111 and 111. So this is how we can separate 3 different type of instructions when we fetch an instruction from a memory into an IR register, and then we will decode it according to its 16-bit of code into 3 parts. Now next is these 3 types of instructions. As I said earlier, the memory reference instructions are 7 different type of instructions. The first one is AND, then ADD, LDA, STA, BUN, BSA and ISZ. And the respective code will be like 000 with 0, 001 with 0, then 001 with 0, that combination in the hexacode form. Similarly, these are our register reference instructions. So we are having 9 to 11 register reference instructions and their respective codes, and same we are having the input-output reference instructions with their code, opcodes, operational codes. Now next topic is instruction cycle. So here we will know about the life cycle of an instruction. How a instruction is fetched from the memory, then how it is decoded and how it is executed after decoding it. That is a lifespan of a instruction. So this is an flow chart for instruction cycle. First of all, it will be fetched from the memory, then it will be decoded and executed. And after execution, it will be completed. This is the hardware diagram from where we are getting that instruction, who will be first initiating that instruction address and how that will be decoded and where it will be going and where it will be executing. So here we are having a multiplexer which will be performing a selection operation among these devices. This is a common system bus diagram, but this is a half diagram of that common bus system because we need only these 4 units for its functionality. So first is your memory unit. This is your RAM memory. Here we are having address register, program counter and instruction register. For fetching a memory from a memory unit, first we need the address of that instruction, and that address is issued by the CPU. First of all, the CPU will issue an address, and that address will be searched in a RAM memory, that is your main memory. So before searching that address will be uploaded in a program counter, and after that it will be uploaded in a address register, and from address register it will be like this: memory address AR. M of AR means the address of some memory content. So from program counter it will be copied to the address register, that 12-bit of address which will be issued by your CPU. So it will be issuing 12-bit of address initially. It will be initiating the process that will be stored in a program counter, and then from program counter it is copied to AR register, and from AR register we will come to know at which location we are having that instruction in the memory, and at that location that particular instruction is searched and then loaded into your IR register, that is your 16-bit instruction register, where we will segregate it into 3 parts, that is address, opcode and the mode bit. From there we will come to know whether it is a memory reference, register reference or input output reference instruction. So this is the hardware diagram for this process, and these are certain instructions, and we are having some timing signal, we can say a time duration in which we have to complete this process. So at time signal T0, we are copying the content of program counter into address register. Means the address which is issued by a CPU to RAM, in that process first that 12-bit of address is stored in the program counter and then copied into the memory content of AR register. That memory content is searched and then that is fetched into the IR register, that instruction of 16-bit on searching that 12-bit of address. And meanwhile, the program counter is also updated. So why we are updating the program counter in this time duration T1? Because when particular instruction is in an execution process, the instruction which is next in the sequence in the memory is have to be executed. So program counter will be incremented by 1 for execution of the next instruction in the sequence. And in time duration T2, we are performing the decoding process. The same process we have done over here. This decoding process, converting the 12-bit of address into these 3 parts: address part, opcode part and a mode bit part, to know among out of 3 which that particular instruction is coming, and for which particular event out of these all instructions we have to execute the instruction and perform the operation on the operands. This is the flow chart of an instruction cycle. Here, firstly, we will start it with the sequence counter. Sequence counter is only to take the care of how many steps are needed to fetch that instruction, then decoding, then executing. That is the number of steps included in that instruction cycle. So at T0, copying the content from PC to AR means 12-bit of address is copied from program counter to address register, and then from address register to IR we are copying it, that 12-bit of address containing some instruction in it, like this. This is your RAM. PC is having 12-bit address. The 12-bit address is having instruction which is stored in the memory of size 16-bit. This is your RAM memory. That address we will found an instruction, and that instruction is copied into IR register of size 16-bit again. Why 16-bit size of IR register? Because we are taking the instruction of size 16-bit in a RAM memory also. That's why the size of IR register is also 16-bit. And then decoding it. Now here, what is the meaning of D7? D7 means we are just taking a look on a opcode bit. As we see earlier, here the opcode bit will be 00 to 6 110, that will be for memory reference. and for this 1 1 and 111, that is 7 binary bit 7 code it is of number 7, 111, 111 and 0 to 6. So D7 means the binary code of number 7. That will be a decision making process. A decision making, we can say, a binary code which will define three types of the difference between three types of, we can say, these types of instructions. So here in this flow chart, we are taking D7 for making a decision among the three types of instruction. If the value of D7 is 1, its value 1 means the opcode will be 111. When the opcode of any instruction in an instruction register is 111, then it may be either a register reference instruction or either a input output reference instruction. Whereas its value 0 means it will be among 000 to 110. That will be 0 to 6 it may be. If D7 is 0, it means its opcode is not 111. It will lie between 00 and 110. So it will be a memory reference instruction. So this D7 is used for decision making among the three. When we come to know whether it is a register reference, input output reference or memory reference, further decision will be taken. What decision will be taken? On the basis of mode bits now. If the value of mode bit, that is bit number 15 in IR register is 1, then it is a input output reference instruction. And if it is a 0, then it is a register reference instruction. Similarly, in a case of memory reference instruction, when D7 is 0, but it may be 000, 001, 010, 110, anything among 00 to 6 binary code. So it may be in a direct phase or in a indirect phase. That will be on the basis of the 15-bit mode bit. If it is 1, it is indirect, 0, it is in a direct mode. So in direct mode, we don't need to find the address of an operand and we directly execute it. But in the case of indirect addressing mode, what we do, we have an address and that address contains the another address. And there we will find actually the location of an operand and then we will execute that operand accordingly. So in timing cycle T4, the execution of memory reference instructions means what kind of operation we need to perform. That will be addition, subtraction, multiplication, division, those type of instruction which will define in the previous chart I have shown you. Similarly, for register reference and input output reference, the execution will be in timing cycle T3. So this is the flow chart for instruction cycle. Now next topic is control unit. So what is the control unit? Here we have two types of control units. Actually, the control unit is used for generating the control signals for performing various operations in arithmetic and logical unit. And the control unit and arithmetic and logical unit combinedly known as CPU, that is the central processing unit in our block of a computer system. So control unit will be of two types, hardware control unit and microprogram control unit. So we will focus on this first one. What is this hardware control unit? A unit which will be made with the help of sequential circuits and the combination circuits to generate the control signals. Now, what are control signals? Like reading operation, writing operation, copying data from one register to another or from one location to another. These are all known as a control signals. Some few example of control signals. This is the block diagram of hardware control unit. So in this diagram, we are having some combinational circuits and some sequential circuits. We are having an instruction register of 16-bit. Again, we have a decoder, 3 to 8 line decoder, a combinational control logic where the actual execution is produced and the control signals are generated accordingly. We have again a sequence counter to generate some timing signals that will be from T0 to T15 for the smooth conducting of these tasks under a particular time duration. And this sequence counter will be of 4 bits. And here we are using 14 to 16 line decoder to generate 16 timing signals from this 4-bit sequence counter. So let's start with this instruction register, which is all happening over here in this hardware control unit. First of all, RAM memory is containing an instruction of 16-bit that I told you earlier, having some address of 12-bit. Which will be issued by CPU. How it will be issuing it? It will be copying it to program counter. So CPU will be issuing some physical address that will be of 12-bit, that will be contained in a program counter, and that address, at that particular address, some data is available. That data is of 16-bit instruction. That instruction is being copied to this instruction register. So this is the starting of this task actually. We directly don't get the binary bit values in instruction register. Initially it is empty. From where we are getting its value, we are copying the content from the memory itself. That is the RAM memory, when CPU is issuing some address of an instruction. So when that 16-bit of instruction will be copied from the RAM memory to this instruction, again it is divided into this 16-bit of format. 0 to 11 is the address portion of that instruction. 4, 13 and 12 will be the opcode bits, and 15 will be the mode bit. That will be storing in a flag that we will named as a I flag. This I flag, and this opcode 3-bit of binary code is converted into 7 outputs, we can say. When the value of opcode is 0, 0, 0, then the binary output of decoder 0 will be functioning. This one. When it will be 0, 0, 1, we can say that will be the code for binary 1. Then it will work for this 1, and so on to D7. So that's why we are taking the value of that decision making bit in a instruction cycle basis on the D7 bit. D7 bit means the decoded bit number 7 of a decoder. From 0 to 6, this 0 to 6 binary code is, if opcode will exist for these binary numbers, for these bits, then it will be a memory reference instruction. And for 7 bit, if it is 1 and all other are 0, means it is activated and other inputs are at 0 state, the outputs are at 0 state, then the 7th bit value 1 will be indicating either it will be a register reference or a input output reference instruction. So this is the decoding process as we have discussed earlier in the instruction cycle. How it will be performed? It will be performed with the help of a 3 into 8 line decoder. And why only 3 into 8 line decoder? Because for this configuration we are considering 3-bit of opcode. So if we are having 3 inputs in a decoder, how many output line we are having? We are having 2 raised power n output line. So the value of n is 3, so 2 raised power 3 is equals to 8. That's why we are having 8 output lines in this particular decoder. And this decoding outputs will go to the combinational logic circuit. Now this decoded output will work along with some timing duration, that is timing signal, that will be from T0 to T50. But before execution we will consider only T0 to T4. After execution we will take T5, T6, T7 and so on. So here for this purpose we have inserted one sequence counter, will be generating a 4-bit of output, and that 4-bit will be converted into 15-bit of output with the help of a decoder again, which will be acting as a timing signals T0, T1, T2, T3 and so on to T50. And if we want to initially set it to the 0 state, the sequence counter, we will press this clear input and it will be reset to its 0000 conditions, mean with no input. And the increment pin will increment its value by 1, and the clock pulse when will be given to it will be generating some output. So when we will be having 0, 0, 0, 0 input as to the decoder, that will be the output of the sequence counter, then the binary output, this 0 will be functional and the T0 timing signal will be generated. Similarly for T1, here the code will be 0001 and this timing signal T1 is generated, and here we will getting a T1 to be functional for combinational and control logic unit, where it will be applied with its corresponding decoded bits, we can say. So this is the brief description of this hardware control unit, and along with it we are having the timing diagram for this block diagram also. This is the timing diagram. Here we are having the positive edge of a clock pulse, that is this one, and the negative edge of the clock pulse, and this space is the area where the actually transmission of data will take place, where the actually operation will take place. So here we are considering only 4 timing unit. Why only 4? Because this will be showing the instruction cycle, the instruction fetching from the memory, then decoding, then its execution, and all that will be completed by T4 timing duration. And here this is your decoding bits. Clear is for clearing the sequence counter. So the rising edge of clock here will be showing the actual functionality where the data is being executed or transferred or getting activated. And this blank line is showing no data transmission during that particular duration. So this timing signal will be measured in the form of clock cycles, we can say, and the clock will be generating it. For example, T0 will be in a clock cycle 1 like this: CC1, CC2, CC3, CC4, CC5, again then CC6 in a sequence. Clock cycle 1, clock cycle 2, clock cycle 3, clock cycle 4, clock cycle 5, and clock cycle 6, and so on until you will be pressing your clock. You will getting a clock signals in a sequence. So again we are taking an example of that previous we can say instruction cycle code, this particular code which we are executing in some timing duration T0, T1, T2, where we are copying the contents of, first in T0 we are copying the content of this program counter, that is a 12-bit of address in a address register. So this operation is being, this instruction is being executed, this instruction is being executed in a timing signal T0. So that's why this process for this executing this particular instruction, this duration is considered, that is 1 clock cycle of duration is considered, and other is blank. Then the next operation is again copying the instruction from memory to I register and then incrementing the program counter. The 2 operations are performing in a timing cycle T1. So this process is shown in timing cycle T1 with a high rising edge of a clock pulse and then stable and then lower down. So this particular duration is showing the clock cycle CC2 and showing the 2 instructions are executed in particular time duration, that is in T1. Similarly, we will have next process in T2, that is the process of decoding. Decoding process, we are converting the 3-bit of op code into 7 decoding bits, D0 to D7, and that will be occurring in a time duration T2. So for this task we are showing it in a T2 timing cycle, which will be in a clock cycle 3. So in clock cycle 1, one task is going on, in clock cycle 2 another task is going on, in clock cycle 3 we will be initiating the 3rd task. In clock cycle 4 we will be executing that instruction after execution, and after that in T3 we are executing register reference instruction and input output reference instruction, but in T4 we are executing your memory reference instruction. That's why we are having a 4 timing cycle for execution process, fetching process, decoding process of an instructions. And here we are having D3 bit that will be showing that it will be in a falling edge for these all clock cycle, and it will be rising from clock number CC4. And here we are showing some clear, initially it will be sequence counter will be at clear condition, means at 0 condition, and for here it will be in timing cycle T4 it will become functional, or somewhere it will be getting lower down. So this is the timing diagram for this hardware control unit, and the timing counter will be generating 4 into we can say its output is 4 bit of, we can say, binary code and 16 bit of timing signals T0 to T15, and it will be incremented after every execution. After T0 it will be incremented by 1 and it will become, now then we will give the value of T1. Suppose we are having 0 0 0 as the output of sequence counter. If we adding 1 in it, it will be becoming 0 0 0 1. So value of sequence counter for timing clock cycle 2 will become 0 0 0 1. That is the binary code of 1. So in a sequential way it will be incremented. So this is all for the today. Thank you. Thanks a lot.